All right, are we good? Yeah. Hi, folks. This is my first Notacon, so let me be one of the probably first to welcome you here. My name is Ethan Dix. Among other things I do during the day, I'm also an instructor at the Columbus Idea Foundry, our hackerspace in Columbus, where we have instructors, classes, tools to rent, things to play with, things to build. And I'm here today to talk about lasers and all the things we use them for, where they came from, and things we can build ourselves with them. So for those that may not actually realize, it's not perfectly an acronym. There's a term for this I've just forgotten, but it's nearly an acronym. It's light amplification through stimulated emission of radiation. And each of those parts is important because that's what makes laser different than just a light bulb or an LED. Is obviously it's light, so we have photons. It's amplified light, and the way it's amplified is because it is stimulated emission, which we'll go into in a bit, and the R, I think, just to round it out. Specifically, stimulated emission is sort of the physics part of this, is where you have the E2 and E1 are states of atoms in whatever material you're lasing, and so you have a photon coming in with a particular energy. That's the incident photon on the far left, and that one photon excites the atom, releases energy, and what comes out is a pair of photons with identical frequency and energy. And that's the important part. They're in phase, they're the same frequency, and the mechanism is you basically bounce things around until you have enough light going out the front that you've got the synchronized light. And that's the important part, is that they're in phase and the same frequency. And collimation is part of that as well, is that they're not just the same color and the same frequency, but they're all going in the same direction. And the combination of all three of those elements make lasers quite powerful for things like illuminating at long distances, for getting the power you need to the far end. So for laser cutters and laser etchers, you're not dispersing, whereas an ordinary LED or just an incandescent light bulb, the light travels in all directions. And so if you've got a 60-watt light bulb, that's 60 watts over a shell, and the shell expands outward. And so the further away you get, the inverse square law means if you double the distance, you quarter the power perceivable at that distance. Whereas a laser, it's all going along one beam, and there's a little bit of dispersion. Nothing's perfect, but you still get nearly all the power. Even if you've doubled the distance, the vast majority of the power still goes to the same spot, just twice as far away. The theory behind lasers goes back to Einstein. After he did his general theory of relativity, after he did the special theory of relativity, he came up with the theory behind stimulated emission and said this should be happening, because he did the photoelectric effect first, relativity, and then this sort of fell out of some of his work. And then 30-ish years later, again, in the theoretical sense, holography was invented, but they couldn't make them. They just simply knew that if we had these devices, we could make holograms, because it takes this kind of radiation, again, synchronized, collimated, same frequency, to produce a hologram. And the very first devices that could make this kind of energy used microwaves, radio waves, rather than light. Those are masers. Those are still in use today in certain communications, long-distance communications things. Laser spectroscopy was the first theoretical application of specifically light frequencies to illuminate a subject and then analyze what that subject is based on what comes off of it. And finally, after each of these theories of if only we had this stuff, we could use it for the following applications, they finally made a laser. And that was, folks may or may not be familiar with, the first lasers were a solid rod. They're called solid-state lasers. And the ruby laser was literally a rod of synthetic ruby, about the size of a pencil, a couple inches long, with a full silvering on one end and a nearly full silvering on the other end. And the whole thing was stuck inside a spiral flash tube, and the tube would flash, and the photons from the tube would hit the ruby, and because of the chemistry of the compounds it takes to make a synthetic ruby, that's a naturally lasing material, that cascade of stimulated emission happens, where as long as the photons that are stimulated happen to be going axially along that rod, they'll bounce off of one of the two mirrors, and they'll go the other direction. And so eventually, as they go back and forth, all the ones that are just slightly off will find their way out the sides, and only the ones that are columnated will end up bouncing back and forth until eventually, because the one end is partially silvered, they do leak out the one end in preference of the other end. So you get a single directional beam from a pulse of light. It's very inefficient, as you can imagine, because if random energy goes in, only a small fraction is going to be traveling that ideal path. But it at least proved the theory, and they did have the first working lasers. But it would take fractions of a second to charge. It was a pulse, and a pulse of laser light would come out, and they would recharge the tube, pulse, another one. And those are the very first lasers they had. Following on the next year, they found a way to stimulate gases to make those lays. And we use those today for higher power operations. For instance, if you're used to using laser cutters or laser etchers, those typically have gas lasers. And then again, just 1 year later, they found a way to take semiconductors, which were new at the time. LEDs were only a few years old, but they found a way to make an LED junction that not only was a diode and emitted light, but emitted coherent light. And we use those all over the place today. A couple years later, they specifically upped the energy from visible light ranges. CO2 laser is important because it's an ultraviolet range. It's an infrared light range laser. And then finally in 1980, much later, they were able to get lasers in the X-ray frequencies to be generated, which is useful for astronomy and useful for certain kinds of manufacturing processes where you're really worried about the frequency of the light. When you're making chips, for example, you need to be able to turn those tight corners on the small features you're making. But most of the work really took place in terms of manufacturing and getting the physics of lasers as we use them today. The bulk of the work really took place in the early 60s, and it took until the late 70s into the early 80s till they really started seeing a lot of commercial application. They became affordable and easy enough to make that we could see them everywhere. Talked about different kinds earlier. The solid state using ruby is one, yttrium garnet is another. We still use YAG lasers for a lot of things. The hallmark of solid state, as I said, is they're pulsed. You have a physical rod of crystal and you pulse light into it, and it produces a pulsed output. Gas, you put electricity in and a continuous beam of light comes out. Various gases will laze. Helium neon is the classic original red laser pointer. Before we had semiconductor laser pointers, classrooms had helium neon red lasers. Argon, CO2, nitrogen is an ultraviolet laser. Chemical lasers are interesting. Those are sort of an offshoot. They're used typically in weapons technology because they involve combustion of a chemical compound to produce energy that comes out as coherent light. So coil is a copper, I'm trying to think what, the C in coil is copper, for example. DEF is deuterium fluoride, hydrogen fluoride, and you're literally igniting. You're doing a chemical reaction, and the output is laser light. Very high intensity, multiple megawatts. Dye lasers are an interesting exception. They came on before semiconductor lasers and after solid-state lasers. They're tunable. By changing the concentration and the kinds of dyes in your liquid, you can change the frequency of light produced from the lasing. And so they're an interesting thing where you can, for instance, in spectroscopy, you could hit a subject with a dye laser and then vary the frequency of the light slightly to get different kinds of data to show up in your return beam. Metal vapor. Same thing as chemical, where in this case, you're vaporizing metal, and the energy in the vaporous gas cloud produces the lasing effect, and then light is emitted. Those tend to be helium and some metal compound, helium-cadmium, helium-mercury. I got helium-cadmium twice there, must like it. Neon copper is another one. The interesting thing, of course, notice is that it's typically much like the gas lasers, it's helpful, although not required, to have a noble gas. Those are the ones in the far right side of the periodic table that have a full electron shell, and just that the nature of those lends itself to the effect. And then semiconductor lasers, like we see in CD players and laser pointers and everywhere else these days, are typically a gallium nitride or indium gallium nitride or some other combination of those compounds that is slightly different than a regular LED, but those all tend to laze quite well for us. And we have a variety of uses of lasers. Entertainment is one of the easiest ones. We see them all over. I've got examples there of laser light shows. going back to the originally, Pink Floyd was a favorite. Laser Floyd was a big deal in the mid-'70s, and I myself attended a Alan Parsons laser show or two in my lifetime. Holograms in the bottom corner. Who here ever saw Logan's Run with Michael York? They had the interrogation sequence where they made a laser of Michael York's head and spun it around, and they had him mouthing the words carefully. Those were some of the earliest color holograms that they had. Down in the lower corner is a standard DVD player laser. Infrared is used for typically CD and audio, data CD and audio CDs, whereas these days for our video watching, we tend to go with Blu-ray, which is really more of a violet than a blue, but it's in the blue frequencies. Took a long time to get that high of an energy of semiconductor laser. Reds and infrareds were easy. Blues are much harder, just like with LEDs. Same issues in physics to work out. And who here has played laser tag? So yeah, a lot of fun there. In science, that's a little hard to see, but on the far side is what's called LIDAR. And just like radar is radio ranging and detection, LIDAR is ranging and detection using light. That's an image of a LIDAR being used. It's a argon laser being shot up to about 100,000 feet to range clouds, ice clouds in the stratosphere for doing ozone hole detection and monitoring. So that is a laser almost the size of these two tables laying on its side in a building, and then mirrors shooting up through a hole in the roof, and they literally go 100,000 feet in the air, bounce off of ice crystals, and are captured back. It's a chopped beam, so in a sense, if you were to slow it all down, you'd see a slug of light. It travels about 1 nanosecond per foot, so I forget how many hundreds of feet long it is, but it's a few nanoseconds of light, goes out of the instrument, goes up to the clouds, bounces off, comes back down, gets read in, and then the next one shoots out. You can sort of see it pulsing. So it's pulsing at a few dozen times a second. And this is definitely what they call in astronomy a put your eye out laser, as opposed to a cut your finger off laser. The blue and purplish one is a laser spectroscopy rig. And the idea there is you illuminate a subject with laser light, you see what returns. Sometimes you also have multiple types of beams you can emit to get different sorts of patterns back. But just like spectroscopy, looking at the surface of the sun, for example, to see what elements the sun is made of by what lines are absorbed, you can illuminate a subject, see what lines don't come back, and you can then determine what the material is made of. And in the bottom corner is a very complicated diagram of something lasers are used for only recently, which is laser cooling, where you can take a clot of cold gas, and by applying lasers in all directions, you can effectively randomize and minimize their motion. So you're hemming them in so that they want to vibrate, but if you keep them from vibrating, they basically shed their energy, and energy of motion we call heat. So if you pin them in, you can cool off individual atoms, and it's how they're doing some of the near absolute zero sorts of experiments, Einstein-Bose condensates and a few other things, by using lasers to extract the heat from a subject. Manufacturing, laser cutters. Top right is laser sintering. I'm sure folks here have lately especially heard of 3D printing. One of the varieties of 3D printing uses lasers, where you take a granular powder, can be metal, can be plastic, and you apply a laser-drawn pattern to the surface. The heat from the laser fuses those particles together, that what you don't hit with the laser stays granular. You then apply a new layer of material, and you hit that layer with a laser, it fuses to the layer below it and to itself, and you build up the item one layer at a time. But instead of like a MakerBot, which extrudes hot plastic, laser sintering takes granular material and builds it up, and you can work in metal, which is very handy. Over on the bottom left is a laser scanner for barcodes and other sorts of things like that. It's a little hard to see from here, but inside the mechanism are a series of mirrors and holographic lenses. One of the interesting properties of holograms is if you take a hologram of a lens, it will behave to laser light the same way that the real physical glass lens behaves to ordinary light. And so when you scan your groceries, the reason why you see the beams going every which way is underneath the counter is a carousel full of different sorts of lenses that are rotated very quickly. And so when you wave your groceries across, it's being scanned 30, 50, 100, 200 times in quick succession. And one of those lasers eventually, when you hear the beep, that's the hardware telling you, One of the pictures it got back, it was able to interpret as a full barcode with checksum and says, yes, I like that number. And you don't know which particular orientation, which time, but because the lenses are constantly rotating and you're also rotating, it gets hundreds of chances to sample that barcode in various distortions and realignments. That's what those are. And it's a little dark to see, but in addition to laser cutting, you can do laser etching. So the numbers on the circuit board were just engraved lightly into the surface, so marking. If anybody here has an RSA tag, for instance, and you turn it over and look on the back, you'll see a serial number and you'll see a date that was laser marked. Communications. There's fiber optic communications is now widespread. It was a big deal to go from copper to fiber, whereas in the old days, if you wanted 10,000 conversations to go between New York and Chicago, you needed 10,000 wire pairs. And with lasers between time, domain, multiplexing, meaning you can take individual conversations, chop them up and stick them on the same fiber, and as well as frequency domain multiplexing, where you can put multiple frequencies of light on the same fiber, you can pack a lot more than 10,000 conversations on 10,000 fibers. And the other benefit is 10,000 fibers is a fraction of the size of 10,000 copper pairs. Top right, you'll see a diagram showing two different kinds of laser transmission through fiber. If you've ever worked in a network operations center and worked with fiber optic network cabling, if it's meant to be used in the same room typically, it may be LED, it might be low power laser, but it's probably what they call multi-mode, which is the zigzag line at the top, meaning that you just basically shoot light in the pipe and it, as long as it's within a narrow confinement, which is part of what the mechanical, they're called terminations. Down in the bottom you can see various fibers and termination ends. They help align the LED or the laser down the pipe, but inside the pipe what's happening is different frequencies, especially if it's LED, may take different paths, and it's not quite a straight line path. So if you've got 100 feet of fiber, mentioned before light moves about a nanosecond per foot, you're actually traveling more than that 100 feet, so it takes a little bit more than 100 nanoseconds to get to the other end because you're taking this longer path. Whereas if you want to move your data between New York and Chicago over a fiber, that's going to absorb light every time it bounces, so you want that to bounce as minimally as possible. You also don't want to waste extra time. You don't want to lose 20 or 30% of your time. So you use single mode fiber, which is harder to build, harder to align, harder to terminate, but you get much more efficient transmission, you get faster transmission, and you see it's a much cleaner looking path. And I'm lumping in laser printers under communication, because we use them to do printed communication. It's an outgrowth of xerography. Xerography was 1960s, late 50s, early 60s invention that was commercially available in the 70s, where if you Xerox something, you take the original, put it on a plate, light is used, you shine on the original, it reflects and hits a charged drum, and where the light hits the charged drum, the charge is dissipated. Where the light does not hit the charged drum, the charge retains. You rotate that past electrostatically attracted powder, sticks to the drum, rolls onto the paper, gets fused down, and you have a Xerox. Laser printing is the same thing. The difference is there's no original. You're scribbling on the drum with a laser to do that charge removal. And I know the first laser printer I used was about $5,000 in the mid-'80s, and now they cost a couple $100 everywhere, every day. They've gotten so much cheaper to use. In security, we've got a variety of things. There's the classic spy movie, light beams everywhere. I don't know how many 60s movies had light beams that the cat burglar had to evade to get to the jewels, to get to the painting, to get to the statue. But and even into the 80s, they were doing that with Tom Cruise and a few other things. But it does work. Has anyone here been to COSI in Columbus, the Science Museum? Has anyone been to the adventure exhibit inside COSI? It was sort of an Indiana Jones-like exploration area. You got one hand there, very good. They have inside there one of the rooms is you've got to get past, they call the Eyes of Scorn. So the doors open as you walk up, and then you step in, the doors close behind you, and they turn on a low-power laser pointer quality laser, and the room is full of mist, so you can see the beam, and your goal is to dodge the beam and get through the room to the other side, to the goal, to receive your reward of a piece of the puzzle. Security in lasers also involves holography, just like entertainment. There's now holograms on a number of currencies around the world, and the same sorts of holograms you'll see on credit cards and software and other things where they want to prove authenticity and identity. And then another interesting use for lasers and securities is for eavesdropping. And a lot of folks don't realize this, but if you're standing in a room, it's not just noise from construction equipment that gets through. Any conversation, we're vibrating the window from the air that we're using to make sound, and lasers are sensitive enough, that whole in-phase thing, you can detect minute changes in distance with that. And by sending a light beam out to the window and then picking up the return and amplifying that small change in the distance between the rig and the window, you can turn that back into sound waves. And I looked into trying to doing a demo, but I could not afford to bring a rig in for that, sadly, because you do need basically for any reasonable distance, so they won't see you doing it, basically a telescope to be able to pick up the reflections off of the window. So laser safety is important. I've worked in a few places where I know people. I unfortunately so far escaped any injury, but I do know people who have certain spots they can't see, and if they go to the optometrist and they show them a picture, it looks like somebody was shooting up the back of their retina with a BB gun, just from various exposures. Laser pointers, the small ones, like these guys over here, these are pretty harmless. You can damage your eye with these, but you've really got to just kind of really get into it and hold it there and so on. It's easier to hurt your eyes by looking at the sun than with a low-power laser pointer. But by the time you start getting into industrial processes, if you're going to be etching or cutting or exposing things, it's higher power, and it's a lot easier to be injured than you think. It's even possible to have eye injuries in telecommunications from not so much the in-building low-power multi-mode lasers, but the lasers used with single-mode fiber. Those are powerful enough to cause eye injuries. So the best thing, of course, is be in places where you're not going to be directly exposed. But one of the risks is if there's anything in the path, metal. So that's one of the reasons why it's important to take off watches and jewelry when working around uncovered lasers. Or if you're moving things around, if there's anything in the room that happens to reflect it back, that can be a momentary lapse, can produce a lifetime injury, because your retina does not grow back. There's eyewear you can get, and I definitely, if you're going to work with anything stronger than anything I've got on the table, I would recommend it. Fortunately, things like laser cutters tend to have interlocks, so if you go to a fab lab or a hackerspace and use a laser cutter, the lid is absorptive, and even if something inside reflects the light, it's going to hit the lid and not get out and not get in your eyes. And as soon as you lift that lid, it's going to cut the power, and the laser is not going to get out and, again, cause injury. But if you're doing your own experiments, building your own things, by all means, pay attention and be careful. So just got a couple little things here to show off. As I said, I was talking earlier with our cameraman here, and I'm sorry I didn't catch your name. Dave. He attempted to make some holograms in the past. I just received this hologram kit. I ordered it some time ago, but my package ended up in, I think it was Pennsylvania, and this guy in Pennsylvania's package ended up in my house. So we got that straightened out, but I did not receive the kit until yesterday. But I can at least show you how it works, even if I can't show you a hologram that I made myself yet. So what we have is a battery-powered higher power laser. This is a class 3A, so it's below half a watt. And it doesn't sound like much, but remember I mentioned all that energy goes to the same spot. Half a watt is quite powerful and will cause eye injury. This is below that. It's the sort of the next step below, so it's more powerful than an ordinary laser pointer you might fiddle with. And it's definitely a don't stare directly at it kind of an operation. The hologram kit comes with a staging stand, which gives you a place to balance a plate, have your subject, and have illumination. And the other purpose of this rig is it establishes an angle between direct illumination and incident illumination, so that you have basically reflected light, laser light hits the subject, hits the plate, And, this is important, laser light directly hits the plate. Because what we're doing is we are capturing on a photographically sensitive plate interference fringes of the difference in the light path between straight path and our obstacle. And if you magnify a hologram, you'll see, it looks like fingerprint ridges, and those are interference patterns. If you look at it even more closely with this kind of rig, you'll see speckle patterns is what they look like, but they tend to organize in random furrows that look a lot like fingerprints. And it's the speckle pattern that's the part that matters. You expose the plate. It takes, with the ones in this kit, about 5 to 15 minutes of exposure. You go into a dark room, open the plate, stick it where this plain glass plate is, hit the switch, and illuminate the subject, and let it go for several minutes. And then when you're done, these are interesting plates. These are nothing like what Dave would have used. In the past, you would literally make up like a wet glass plate as they did 100, 120 years ago for regular photography, and you would treat it like you would treat any piece of film, totally dark room, expose your film, develop your film, and then stabilize your film, all the standard chemical baths. This has a proprietary, so they don't tell you what it is, chemistry in it, so they're dry plates, and you basically can't overexpose them because the act of exposing consumes the chemicals in the photosensitive layer. So as long as you basically open the box in a dark room, set it up, and then only either use low red light, like they provide a little red LED flashlight. You hit it with the laser so that they're less than 1%. This LED flashlight is so minimally powerful it can't trigger the chemistry, but a regular room light could. But the intense light comes out of the laser, exposes the plate, and if you leave it on for 20 minutes instead of 15, it doesn't overexpose the plate because the chemicals are already all used up. But the important part is you can't move anything. And I don't know if this may have been Dave's problem. You can't speak. You can't move. The room can't shake. For instance, I wouldn't want to try to make it in here with that noise going on outside. That's too noisy. That much vibration will cause these tiny interference lines to blur. And unlike a shaky camera, where if you take a shaky picture, it looks like what you took a picture of, but just doesn't look very good. If these interference lines overlap, you get no hologram. You get no image at all. So it's not just it looks bad, it just doesn't happen, which is what you had, which is why I think that's what happened. It is actually difficult to do holography. They've simplified this by giving you a fixed space rig, and the instructions say every page, do not talk during the exposure. Do not move in the room because the act of literally going back and forth causes air currents. Turn off the air conditioning. Air handlers will produce air currents that will produce enough vibration to ruin the effect. Those interference lines I mentioned, you can pack 50 of those into the width of one human hair. So any vibration of a fraction of a hair on the glass plate, on the subject, on the laser, will ruin the effect. But that said, if you can get a stable place, quiet place, a dark place, I'm looking forward to making quite a few of these. Oh, something else they recommend is, because it's a red light, they recommend a red subject. If you use a blue or a green subject, it's not going to show up very well because it will just absorb the light. It won't reflect the light onto the plate. Because again, you're going for that difference between direct path and indirect path. And then to expose it, to reveal it later, once you've actually made the hologram, you simply take the object out, and in the same arrangement, at the same incident angle, what happens is you now have fresh light only from the laser hitting your plate, and what the result of that is this light hits the existing interference patterns, and those provide constructive and destructive interference, and what falls out is the image of what used to be here. So the combination of light from here and light from here make the interference. The combination of light from here and the interference reproduce an image of the object. And let's see, what do we have? A little bit of time, good. This is just a little toy. There's various kinds just like it, but it's a little laser toy game. Whoops. The original gameplay is you're meant to set up and take turns placing the mirrors and doing various things. And the idea is you want the little laser pointer here to trigger off light to And these are hard to align. Yeah, well, this is only meant to go for a burst. It's a time pulse. So I'm going to try this from here. I mentioned before about the distance. You're meant to play on the table and work in here and turn these around and take turns placing these. But over here I have just an ordinary laser level, the kind you would do you'd use at home in construction. And if I've got this lined up right, there we go. So, like I said, distance, the power, no problem. Run it through a little bit of a light path, easy to work with. Last thing I wanted to mention is if you do get into experiments, one of the fun things you can do is work with putting mirrors on speakers, putting mirrors on motors. If you remember the older laser shows, like the ones in the middle, they tended to be a single color. They weren't the newer, fancier, multicolor laser shows, and they tended to be lots of what they call lithograph figures that you would see on oscilloscopes as well. And those are quite easy to make. You effectively position one galvanometer, as they're called, or one mirror that you can change the motion of at one angle, and you place another one 90 degrees to it. So the idea is that the laser comes in this way. The first device only changes light on the y-axis, for example. The second one is oriented so that it only changes light on the x-axis, and the combination of the two, you get sort of a zigzag light path out the other side of the box, and you can do things like, if it's on a motor, you can have them spin and wobble, and you get one to wobble up and down, one to wobble side to side to get those sorts of figures. Or if they're on a speaker cone, you could, for example, play a sine wave that will cause the speaker cone to go in and out, and you change the phase and the frequency relationship between the two speakers, and you get different patterns in the light. And that's how they did those shows 30, 40 years ago. And it's not really that hard. There's plenty of places to look on the internet for how to build your own laser light show box with a single laser. But one of the important parts about those is if you look at a regular ordinary mirror at home, you're looking at the glass front face, and the silvering, the reflective layer, is on the back side, and that's to protect it so you can clean the glass and you don't scratch the reflective coating. The problem is, if you think about a laser going through it, the laser hits the front of the glass, and because of the difference, it's called an index of refraction, between air and glass, the light takes a little bit of a bend, then it hits the reflective layer, reflects, hits that air to glass barrier again, and changes direction again. And what ends up happening is it scatters the beam. So effectively what ends up happening is one beam goes in and three beams go out, a primary beam and two ghosts. And the way to fix that is you use what's called a front surface mirror, where the reflection is on the side you're looking at. They're touchy, you can easily scratch them, they're hard to keep clean, and they can be expensive, but if you ever have taken apart an ordinary flatbed scanner, one of the things you'll see in the scanner is a handful, 2 or 3 or 4, strips of mirror that are used in the scanner, and because they also don't want to have ghosting going on, it's all front surface mirror. And so literally, I just harvested these hunks right out of an old HP scanner, and let me see if I can get this to work. I'm going to try to project some on the ceiling and show the difference. There's a nice dot, and that's the front surface. Oh, nope, I'm backwards. This is the front surface. And that's the back surface. Unfortunately, it's really hard to tell the difference because my hand is shaking, but if you were to look up close, it's a little easier to see at the mirror. So sadly, this isn't working in a room that's this bright. But the effect is real, and if you get to a dark room and you work with it yourself, you can tell the difference between which side the mirror is facing and which side is not. So that's what I've got for demos. Whoops. Questions? And where's our guy with the? There you are. Anyone? Questions?
General comment you hear about the new weapon that the Navy just put in? Actually, military deployed laser to shoot down aircraft.
I did catch a little bit about it, but I didn't read the details. I did read that the Navy was planning on beginning to equip vessels with anti-aircraft lasers was imminent.
They just deployed the first one, I believe.
Far out. Anybody else? Questions? Anybody awake? Well, I guess we've got a few minutes, so if anybody wants to come up and have a look at things a little closer, it'd be a good time for that. Thank you for your time. I hope you enjoyed it.